We're now going to learn all about the Fundamental Theorem of Calculus Part 2. The Fundamental Theorem of Calculus Part 2 provides a direct method for evaluating a definite integral using antiderivatives. This is going to be a lot easier than having to use Riemann sums. Let me just remind you what the Fundamental Theorem of Calculus Part 1 tells us. It tells us that if we have a function g of x, which is the definite integral from a to x of f of t dt, then dg dx, or g prime of x, that's just the derivative of g, is equal to f of x, which is the integrand evaluated at the upper limit of integration. Since g prime of x is equal to f of x, we can say that g of x is an antiderivative of f of x. To get to the Fundamental Theorem of Calculus Part 2, we have to complicate this a little bit, and we're going to let a function capital F of x be any antiderivative of little f of x. And what we're going to do is we're going to compare this to g of x. Since any two antiderivatives differ by a constant c, we can say that capital F of x minus g of x is equal to a constant c. We can then rearrange terms and say that capital F of x is g of x plus c. I'm going to put a red check here because we're going to come back to this a couple of times. What we're going to do now is we're going to see how we can use the expression that I marked with a red check and the definition of g of x in the green box above, right here, to find a formula for the definite integral of f of t from x is a to x is b. So our goal is to find a formula for our definite integral, and that way we won't have to keep using Riemann sums. How we're going to do this is we're first going to let x be equal to a. This gives us that capital F of a is equal to g of a plus c. We're just substituting in that x is equal to a. This function here comes from our green box up above, and that's what g of x is equal to. Now we're going to let x be equal to a, and notice that a is now in our upper limit, and we're integrating from a to a, so that integral is equal to 0. And we can say that f of a is equal to c. Let's put that in our pocket for a minute, and we're going to come back to it. Now what we're going to do is we are going to let x be equal to b. So let's come up here to the right, and we let x be equal to b, and we get capital F of b is g of b plus c. Now, we know what c is, and we can substitute in that c is capital F of a. Now what we're going to do is look at this formula for our integral, and we're going to let x be equal to b. And that gives us that g of b is the integral from a to b of f of t dt. Hang with me, we are almost done. What we're going to do is we're going to take this expression and put it up into that equation. This gives us capital F of b is the integral from a to b of f of t dt plus capital F of a. Now all we have to do is just switch around terms. We'll pull the capital F of a to the left, switch the sides, and we end up with the integral from a to b of f of t dt is equal to capital F of b minus capital F of a. And that's exactly what the Fundamental Theorem of Calculus Part 2 is. The Fundamental Theorem of Calculus Part 2 tells us that if f is continuous on the closed interval from a to b, that's super important. The theorem does not apply if f isn't continuous on that interval. Then the integral from a to b of f of t dt is equal to capital F of b minus capital F of a, where capital F is any antiderivative of little f. In other words, it's a function such that the derivative of capital F is equal to little f. I'm going to now say this in a way that makes it easier when you go to use this theorem. Our theorem tells us that the definite integral of a function equals the antiderivative of that function evaluated at the upper limit minus the antiderivative evaluated at the lower limit. And that's all there is to it.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.